Hi, and welcome back to the Frontier series. My name's John, this is my colleague Nora, and we're continuing our conversation with Tom and Henry on their paper, Learning is Forgetting, LLM Training as Lossy Compression.
Maybe this would be a good time to go into kind of the methodological details of how you did all of the work in the paper. So you're using the information bottleneck framework, and from my understanding, that was originally for use cases where the input and the target are different. So you mentioned labels or different languages. And here you have kind of continuous text. You're using n-grams, so arguably same distribution. So walk us through kind of how you, what decisions you made along the way to make this a tractable problem, and how you did it.
Excellent question. This is a question that slightly haunted us for a while. It's very difficult to work out.
There were a lot of long chats over a whiteboard with deep frustration at the difficulty of maths.
You're right. This is like a general thing in sort of information theory when we're talking about compression, but like particularly in an information bottleneck context, where you have a notion of a source distribution, the input, and you have a notion of a target distribution. And critically, if you think about what we're talking about as the compression phase, this is something where you decrease the information that you have about the input without decreasing the information you have about the output. Mm-hmm. And in order to do that, your target and source need to be different. You need to be able to compress one without also compressing the other. Right. And this led to this question of like, okay, in a language modeling context, what is the target and the source? Right? It's essentially this question of like where the sort of moving head is in the model as you're dealing with a sequence. And so what you can see in the paper is that we sort of do this with an n-gram modeling approach, sort of like an old school NLP, like we can't condition on the full context window, so we'll use finite widths of context as an approximation to that. And what's interesting is when we look at just token level backoff, so just going information with the current token and the next token, we get this very clean sort of like 7 pattern where you can compress your like input, you can compress the source independent from the target. Mm-hmm. And if you think about language, that kind of makes sense. For a moment, let's assume word level tokenization. If I know that the current word is an adjective, mm-hmm. that almost definitely has to be preceded by a determiner, like the or a, mm-hmm. and it almost definitely has to be followed by a noun. Right? And so at the individual word or token level, you do have really distinct leading and trailing distributions. And if you were to permute individual words in a sentence, you will immediately make it ungrammatical. You can't just scramble individual words. Yeah. But as we increase the width of the context, things become more and more interchangeable, right? Mm-hmm. Where if you shuffle 2 words in a sentence, ungrammatical. If you shuffle 2 sentences in a paragraph, it will probably be harder to read, but it won't necessarily be wrong. Mm-hmm. If you shuffle 2 paragraphs in a document, similarly, you might actually not impair readability at all, depending on how those paragraphs are structured. And so what we see when we look at the compressive patterns is as you take more context into account, it becomes harder to compress your input without also compressing your output. And so we see these traces of these compression patterns where when target and source are really distinct, you get this very nice sort of like approach to the bound. Mm-hmm. And as they become more interchangeable, you wind up sort of like moving along the bound, still getting closer to it, but you're sort of going down in both because it's harder to compress one without also compressing the other.
Yeah. And would you like to walk us through kind of how you prepare the data to be able to compute entropy and entropy obviously requires the discrete distribution. So how did you prepare? You're using embeddings across the layers. So just walk us through kind of what the process is there.
Is this me? Is this my territory?
Do you want me to?
It's so preparing the data, it's just C4. And so it's like each example is a web page. And then it's just passed into the model for its tokenizer that it is built with, that it comes with. And then in terms of the embeddings, going back to sort of where we started, where what we're really interested in is this approach to interpretability that is across the entire model. Mm. we don't just take the final token representation in the final layer, which is what a lot of interpretability work does. We take every single token representation in every single layer of the model. We then do this soft quantization procedure, which is relatively fiddly. If you would like graphics and visuals, you can find those in the paper. But it's essentially a way of converting this continuous high-dimensional space into a categorical distribution. And once we have that, it's pretty straightforward to estimate entropy and mutual information, sort of using Shannon entropy rather than some continuous analog. And so broadly, this sort of methodology is taking reams of data, pages and pages from the internet, converting that into these categorical distributions at every token and every layer, and then aggregating so that we can get a single model level statistic that says, hey, across this entire model, regardless of its size, regardless of dimensionality and number of layers, we can tell you in one scalar value how much information is in this model about its input, and how much information is about the goal, or how much information is in it about distinctions like, say, preference.
Yeah. So during the soft quantization procedure, you're normalizing the vectors and you're kind of bucketing them. And so you're throwing away the magnitude. Do you think there's anything in there that is important for improving the compression estimate? Or do you think it's information that you can afford to lose, such as like frequency-based or...
Yeah, I mean, so great question. This is something where I'll say, from a methodological perspective, it is very convenient to normalize. This is something where previous entropy estimates that do not do this, you have to estimate the support of the distribution. And so you have to know where all of the embeddings lie. And that requires passing through all of the data so that you can estimate the support. And then once you have the support, you pass through the data again in order to get your discretization. And at LLM scale, doing multiple passes through the data is not a thing that we would like to do. And so normalizing means that everything lives on the unit hypersphere. And so we know the support. The support is the sphere. And so there is, like, I'll flag this as like, it is methodologically convenient. That is part of the picture. But exactly as you're saying sort of about frequency stuff, from a variety of work in NLP over like the past 5 years, there's this sort of result that recurs with some confidence that shows that what the norm is encoding is something about the frequency of the token in the training data, which makes sense if you think about the way that attention works, right? Where like the word "the" appears constantly and does not have an enormous amount of information. And so when your model is doing its sort of self-attention, you don't want it to just keep attending to "the" and filling "the" with what the embedding is sort of made up of. And so "the" winds up having a really small norm, so that even if you attend to it, it doesn't overwhelm the other information. And so what work has kind of shown is that you can conceptualize what the magnitude is doing as encoding something akin to the frequency in the training data, whereas these angles are encoding something more like the sorts of semantic relations that we're interested in. And so in future work, we would like to better understand what the norm is doing, maybe verify this stuff within our information theoretic framework. But this is our mental model of why this still works without that information.
Yeah, that makes a lot of sense.
I think it's worth saying that the dimensionality of these embeddings is pretty high, right? It's in the thousands.
Tens of thousands sometimes.
Tens of thousands. And when we do this normalization, we are throwing away one of those dimensions. There are still, if you view it as kind of going from Euclidean to kind of polar coordinates, in the polar coordinates, the radius is only one of the coordinates, and the rest are all the angles. So we're only really losing one dimension from this extremely large encoding. So chances are, maybe this isn't true. Maybe there's a lot of information in the radius. It seems, I believe there's work out there showing that that's not the case. And that at least in transformers, most of the information is in the kind of angular component. But just from if given that we're talking about kind of lossy compression, it would be very, very surprising if the model learns to compress all of the information in one of the coordinates and not in all of the kind of 999,000 other ones.
Yeah, absolutely.
I guess a quick follow-up on this, right, is when you sort of project them into this onto this unit sphere, I've noticed that to do the discretization, right, you randomly sample vectors as these sort of nodes that are sort of sticking out. And something that stood out to me was, if I was approaching this, I would have sort of tried to go for like an equispaced thing, at least intuitively at the beginning. And I'm wondering what the advantage of like randomly sampling them.
So I think the the tricky thing is that, so firstly, we don't necessarily want to accurately represent the original representation. We're interested in how spread out they are.
Right.
So that is a very kind of coarse measure. And ironically, for a paper about compression, we're happy to throw away a lot of that information to get it. So it doesn't matter that we're kind of not accurately fully representing the entire complexity of the representation. The other part is that I think our intuitions about space fail in high dimensions.
Yes.
And again, these representations are crazy high dimensional. And the notion of kind of spread out is very difficult to kind of even reason with. And the number of, because there are so many dimensions for representations to hide in, to have a kind of full coverage, I guess, the number of anchor points or bins would need to be really quite high.
Yeah. Well, just a quick comment on that as well. When the dimensionality is really high, as you say, our intuitions break down, but also if you randomly sample, it's very likely that the vectors are orthogonal. So you kind of end up having doing some form of that.
I'm sure there are analytical results about this, but like you say, the chances of you finding kind of anchor points that are close to each other is vanishingly small.
Yeah. And I think, so to your point, I would also love it if we had a perfectly uniform grid.
Yes.
It turns out that is very fiddly to do, particularly in high D spaces.
Sure.
And so I can say that part of the intuition for like where this approach to entropy came from, this is part of my thesis is sort of developing this idea, was trying to think about what is information in a continuous space. And there's some lovely work from Jaynes in 1957. He's a physicist responsible for the maximum entropy principle, who has a delightfully petty paper that he writes, where he observes that Shannon came up with differential entropy, which is the general purpose continuous analog for entropy, by simply swapping the sum with an integral and assuming it was correct without deriving it. And he observes that it is in fact not correct. And this winds up popping up in a bunch of different places where if you compute the differential entropy of a Gaussian and then another Gaussian that you dilate, so they're both Gaussian distributed, but one is a little bit more spread out. They will have different entropies. And if you have a uniform distribution over a tiny support, it could have a lower differential entropy than either of your Gaussians.
Yeah.
And so you wind up in this weird place where, like, in the discrete case, entropy tells you how uniformly distributed things are. For differential entropy, you're getting this quantity that is this sort of hybridization of both skew and spread in space. And so what Jaynes says is like, look, the way that we should really be thinking about entropy in continuous spaces is as a kind of divergence, where what you want is you want to have a uniform distribution over the support, and then you want to have your distribution of interest. And if you take a KL between those, that's going to tell you how non-uniform your distribution is, regardless of how spread out it is. And so given that as context, you can maybe see why we take these uniform samples on the surface of the sphere, right? We can think about the embeddings from the model as samples from the distribution of the model's like representational space. And our uniform samples on the surface of the sphere are these samples from our reference measure, from this uniform measure over the same support. And so, yeah, it would be nice if we had an actual sort of exact uniform distribution. But we have some analytical results that give us sort of pretty good bounds with a relatively low number of bins. The bin randomness is not necessarily a problem, particularly at the scales that we're working at.
Cool.
So I guess something else about this is, I think it's a really good point to mention that we are interested in a comparative measure, and we're essentially trying to work out where on the scale between completely uniform, kind of completely random, and a delta function, like a point, where are we on that scale? And otherwise, we don't really care. And the other crucial thing to point out is we want to do this at different scales. And we want results to be comparable whether you're in kind of 2D space or 1000D space. And doing that requires kind of essentially jumping through a bunch of hoops to say, okay, if you, like you say, if you sort of naively compare the uniform distribution in 2D space to a 1000D space, they're not comparable. So you have to do some work to make that normalization, make that comparison valid.
Yeah, I wouldn't say a bunch of hoops. I would say one very beautiful hoop built by our friend Julian, who did an excellent job, which is essentially a way of making estimates directly comparable. We use a softmax in the entropy estimation procedure, and it's a well-known phenomenon that you have this concentration of measure phenomenon, where we're taking a softmax over dot products, right, or cosine similarities. And we know that in really high dimensions, sort of everything winds up being like, you get this reduction in how spread out those values are. That's sort of what concentration is here. And this is known in sort of the self-attention mechanism itself, where they take the dot products within attention and they scale it by the square root of the dimensionality. And that is the correct sort of leading order scaling factor if you have sort of two distributions which are directly comparable, which when you're like using the same dimensionality and it's in a self-attention mechanism, that makes sense. We do something similar where you can essentially have an analytically computed temperature or scaling factor in your softmax, which means that regardless of the number of anchor points that you use and regardless of the dimensionality of the model, all of the estimates are like for like comparable. You can put them all in the same graph and they have meaning in relation to each other.
I'd love to learn more about whether you explored, so you aggregate over all the layers to obtain this metric, but I'm curious whether you observed or whether you explored this kind of development through the layers. Obviously, initially the model is kind of doing very easy kind of lookup. Towards the end, it's very task-based, and there are a lot of transformations in between the layers. So I wonder whether you explored how this compressibility varies and whether there are certain layers that kind of doing the heavy lifting, or whether you explore the dynamics through the layers.
So I've forgotten.
Okay.
Off the record.
I mean,
I feel like we did this right.
Yeah. So there's
nothing.
We didn't find nothing.
Do you want to?
Yeah. There's a bunch of different plots to this effect. Essentially, you have this broad pattern where you wind up having somewhat intuitively more information about the thing that you're going to predict in the later layers of the model. Right? As you progress towards the output projection, you have more information about the thing that you're going to project to. Right? But I think to your point, I think that your point is maybe inspired by a lot of mechanistic interpretability work, which is trying to dissect, okay, this part of this layer does this individual thing, where you can see sort of a binding behavior, or you can see that this is where like, I don't know, toxicity is encoded, or all of these sort of fractional things. And that is something that we're sort of looking at now, but what the paper that we're sort of here at the conference presenting is about is it's sort of this very zoomed out picture. And so the answer is that like, for the analyses that we did about just the input distribution and the output distribution, the layer-wise results are not particularly exciting, right? Where it's sort of, as you would expect, layer by layer, you get a slow, gradual transformation into the thing that you're kind of trying to predict. Now, what is probably the case is that that slow transformation is driven by a bunch of interesting sub-processes, right? Like we kind of know that early layers in a model likely do something like part of speech identification. We know this is a verb, we know this is a noun, and then role structure identification. This is the subject of the sentence. This is the indirect object. And so you can see as you move layer by layer, you might get higher mutual information with respect to those abstract classes. But when you're just looking at it from this sort of zoomed out 30,000 feet picture, it winds up being that, hey, input information sort of degrades a little bit. It doesn't degrade that much. I think the residual connections help to sort of keep input information throughout the model. But you get this gradual increase in sort of information about your goal as you move through.
Okay,
I
interesting.
guess it kind of intuitively, ultimately the model as a whole is trying to solve the task. And it needs to, like every layer is in some way trying to predict the output. So it'd be very surprising to me, firstly, if any one layer decided to just throw away a load of information, because ultimately the output of that layer is then used as input to the next layer. It can't recover it. So it like every layer has to be contributing to the final prediction. I think the other thing is that it would also be very surprising to me, given the way these models are trained, although they're very high parameter count, the data set is also extremely high.
Mm.
Like there is a lot of information we're trying to get into these models. Traditionally, we train these models with dropout. The chance of getting a kind of concentration or a really aggressive concentration of, let's say, kind of work in any one specific place in the model would be really surprising and strange.
Yeah.
And we kind of explicitly design the training setup to avoid exactly that. Like it's a model where one layer does everything and another 3 layers do nothing is probably not going to be a good model.
Yeah, no, absolutely. No, that makes total sense. I was curious whether there are some layers that represent information in a more compressible way, whether there's like dips or it's fairly kind of uniform.
I think it's relatively uniform.
Mm.
I think that this is maybe sort of an important distinction in the way that we talk about compression and the way that we talk about information here, where what we're talking about are these mutual informations.
Yeah.
So for us, compression is how much information you have about the input,
Mhm.
right? In a lot of other notions of compression, in a lot of other work over the past year, compression is talked about as spread. This is maybe just standard entropy, how uniformly distributed you are. And so I think there are results that talk about, say, the rank of the different layers as you move through the model, and maybe some are lower rank or higher rank. And that may be the case. That's sort of like, we have a CSV file that would tell us that. We have not looked at what that CSV file says. But for us, because we're not actually talking about these shifts in relative rank across layers, we're talking about whatever your rank is, how much of that variance is explained in terms of the input. We're able to say that that figure is relatively stable and moves very smoothly through the model.
Cool.
Yeah, again, I think driven in part by the residual connections, but it's also like, it would be surprising to me if, with the level of sort of like abstraction we're working at, if across thousands and thousands of documents from the internet, across like tens or hundreds of thousands of tokens within those, you got really sharp spikes in that aggregation process. That I think would be kind of surprising in these models. I think probably a lot of the optimization going well is having this all be kind of smooth, having it not necessarily be like a hugely stochastic movement from layer to layer.
Cool.
That makes sense.
So I guess I want to talk a little bit about like the practical implications of this, right, for training models. So the first thing that comes to mind, right, is that we have this two-phase thing. And so when we train models with next token prediction, we wind up doing this 7 thing that this two-phase 7 shape in the two-dimensional space of complexity and expressivity. That's clearly not the like shortest distance through this two-dimensional space to get to the bound, right? Is there any perhaps way that maybe you could use the results that you have here and perhaps train directly on this optimality, like, or would that make some extremely strange model? Like, what are your takes on this?
Interesting. I think I feel like this comes back to something we talked about earlier with the kind of the fact that training is ordered. And I guess my intuition would be that in order to know what you need to keep and what you need to throw away, you kind of need to first learn what it is you might throw away. So it's, I guess I can't immediately think of a way in which you could kind of skip that. You first have to learn like what's going on, and then you go, right, okay, these are the bits that recur, these are the bits that don't recur. But until you have that kind of high level view, I feel like it doesn't make sense to go, knowing what to ignore in the first place. I mean, maybe that's the way to frame it. I guess perhaps it comes down to sort of data set selection. Like if this is a comparison we could potentially do, is say if your data is higher quality in some sense, maybe the reach of that 7 is kind of slightly reduced, and you kind of there's less information in the data set that you end up discarding.
Yeah, I mean, I think it would be really nice if that worked, right?
Yeah, obviously.
That would be very handy. I think for reasons that you mentioned, but also for reasons that we talked about earlier, I think it's unlikely that works out of the box, right? As we were saying, if you know exactly what the priors are, you could build a better model, and then you wouldn't need to be doing deep learning. And so I think the idea that you want to be optimally compressed is truly abstract, but there are so many different ways to compress that just optimizing for compression in its own right, I think, would not necessarily give rise to the kinds of rich semantics that we have here.
Mhm.
Where I do think maybe from an optimization perspective it could be useful is for these kinds of finer grained downstream distinctions, like preference is interesting, where the way that we get that information into the model now is really inefficient, like reinforcement learning is a giant batch size on these huge models, in order to sort of optimize for this binary reward signal. And you could see a version where, okay, we've already done the heavy lifting of getting this pretty good compression of the internet to begin with. Let's now permute that a little bit in a way that is more controlled.
Mhm.
But the way that I see this sort of like being useful, and part of the reason why we sort of started down this line of work is in 2026, evaluation is really hard. And so if I have 100 different model candidates, it's very possible that they all put up almost identical scores on the benchmarks of record. And you have to believe that one of these would be better to release or to have people use than the others. But because we don't have good evaluations at this scale, as we've said, the notion of what it means to be out of distribution is weaker and weaker as time goes on. It becomes this question of, independent of a particular evaluation, how can I actually tell if a model is better? And so part of what this project is about, and this approach to interpretability is saying what geometry is better, right? What are the representational structures that drive behavior, rather than just talking about behavior in its own right? And I think if we can articulate this notion of optimality really cleanly with respect to training distributions, but also particular task distributions, it allows you to say, okay, well, given all of these perform equally, let's pick the one that's more optimally compressed under an assumption that that is going to be more robust in ways that we lack the ability to evaluate at present.
Yeah. Evaluation, so I guess for kind of a bit of a digression, but a lot of my current work is on model merging. So model merging is a very cool technique. One of the, I won't go into detail because it's kind of a sidetrack, but it's a very fast process to apply. And when we want to apply model merging, we can kind of generate a bunch of potential candidate models using this process extremely quickly. The problem is evaluating them. And in model merging, you're just averaging some parameters, no gradient, there's no data, extremely fast. But you then have to evaluate your candidates. So the bottleneck on merging is an extreme example, but this is kind of true of other training processes as well. If you're trying to do hyperparameter optimization, you have a bunch of candidates, you need to work out which of them has succeeded. And evaluation is this inherently, I kind of think of it as like it's a discrete process, right? You can only sample one thing at a time. The output is literally discretized as tokens. Quite often the scoring signal on that output is itself discretized, or if it's continuous, it's kind of fake continuous. So the point being that the signal is very kind of noisy, very slow, and if you are trying to make fine-grained decisions about quite similar models, it's easy to compare models 3 years ago to models now, right? The differences are huge. If you are in a kind of production setup and you're trying to select which model you think is best, they're going to be pretty similar. They're probably pre-trained with the same data, probably post-trained in similar ways. You're getting a very fine-grained granularities. And at that point, a decoding error or some kind of stochasticity in your evaluation setup is going to potentially start to dominate. Apart from which, it has very weak guarantees. If you are, if you're asking the model if you're evaluating the model and how it behaves, it doesn't necessarily tell you that much about how it's actually working. And I think, part of this is getting it kind of, instead of trying to evaluate what the model looks like, get at how the model is actually working, how it is making those decisions. And it gives you, if nothing else, it gives you some degree of confidence that, yes, you probably want the evaluations to be good as well, but given a set of candidates that evaluate equivalently, you probably want the model where you have some stronger confidence about how that is being done, how the information is represented. Is it
behavior
laid
doesn't
out in a good way?
necessarily tell you about representational structure, right?
Absolutely not.
Where it's like, as we were talking about earlier, if you have specific data, a lookup table is a really good way of solving that problem. And so let's say that we're producing an LLM, and entirely accidentally, through no one's fault, the evaluation data gets mixed in, and we've mixed in MMLU Pro to the things that we're
That will never happen.
It would never. No one would be so
Accidentally.
Absolutely never.
then it will turn out that that model is going to be really beautiful on the benchmark, when I don't necessarily think that that is going to be indicative of any meaningful greater robustness or greater ability downstream.
We can be pretty confident that is not going to generalize.
100%. And so what's frustrating on some level with all of this stuff is that like these deep learning models have become ubiquitous across tech, but also across increasing areas of our life. And yet we do not talk about their representations, right? We make almost no design decisions during training based on any statistic that you compute over the embeddings. You just take downstream behaviors as the signal because we lack a sufficiently useful way to actually characterize these structures, which like makes sense. We are humans, and I don't know about you, but like I don't have a good mental model of 12,000 dimensional space. Like I struggle past 3. And so the idea that we can look at those spaces and make meaningful decisions about what we should be doing during training is on some level sort of like absurd. But we also know what we just said, which is that behavior is a really bad proxy for whether or not the model has meaningfully learned something. And so it feels like on some level, if we want interpretability to not just be a loose bag of facts that we have happened to collect, where we go, hey, this part of this model does this thing, maybe this is how this happens, but is actually something that is efficient enough to compute during training and can give us these heuristics that are sort of powerful about whether or not we have a good representation. That in terms of model selection, but also stopping criterion and picking the data distribution that maximally increases the kinds of information that we want in the model, that gives a feedback signal that behavior just simply can't. Predictions and evaluations just can't do. And that's really hard to get. We've put a lot of work into having some summary statistics that have that predictive power, and we think we have a framework for doing that. But like, yeah, at this point, we're trying to see how well we can use that to actually manipulate or make these sort of decisions that you have to when you're putting together a model.
I think it might be useful to make this a little concrete and say, you know, this is we're now into territory where it's not in the paper, kind of speculating, but we might consider calculating these mutual informations with respect to other labels. So we do it with human preference, we do it with tokens, but there's a lot of kind of quite natural separation. I kind of think of them as decision boundaries, I guess, in what we're trying to do that would be really interesting to look at. So one example I kind of keep coming back to is the idea of language ID. So if the problem you're kind of considering is translation or working in a kind of cross-lingual context, you would like the model to respond in the language in which you've asked it to respond.
Yeah.
And you can probe this behaviorally. You can say, here's a sentence, translate it into French, translate it into whatever. And then you can sample a bunch and go, okay, yeah, it looks like it, based on the samples that I tested, it did indeed respond in French. It's a very weak, there's guarantee is a high bar, but it doesn't give you a lot of confidence that it's always going to do that. Was there some bias in the data you used to test that? Was your evaluation technique correct? So one nice thing to do might be to say, okay, how good a concept of language ID does the model have? And that's not in terms of kind of behavior. It's does the model know what it means for different languages to exist? Yeah. Can it do the internal representations align with language ID in some sense? And to me, this gives you potentially a way of measuring how well the model encodes language ID, and therefore how well it is going to work downstream in future across a much broader set of contexts. And you can imagine a whole bunch of different categorizations. Code language, for example. We've talked a bunch about kind of safety, harmfulness. Human preference again is another one. Does the model know what it is being asked to do? I guess.
Yeah, definitely.
Yeah, and so I think, this discussion around how this is useful or what the impact is, I think does get to sort of part of why we're proud of the work that we have here, is that, like, to be clear, the claim that a model is a compression of its data is not something we have come up with. I think we were beaten to the punch by like 100 years.
Yeah.
I think that's kind of implicit in the definition of a model, right?
Sure.
And the idea that an LLM is a lossy compression of this enormous amount of data that it's been trained on, again, people have said that. It turns out that that is very difficult to quantify. And it turns out it is very difficult to get those kinds of statistics about how good your representation is at arbitrary scale. And so what we've started looking at is how you can do that at scale in a way that still has theoretical implications and aligns with these intuitions that we know have to be true. But yeah, the picture that we're painting here, where we talk about language ID and code ID, paints gets at the core problem that models are huge. The amount of information that they need is enormous, right? And so here we're able to talk about like just broadly input and output distributions, but moving forward, it's like, models need so much information and they need very specific kinds of information for specific tasks. And so it's understandable that training them is really complicated, and understanding the representational signatures that good training gives rise to, I think, is a complex problem, but is what interpretability should really be focused on.
Yeah, cool.
Yeah, really well said.
I guess the other question, kind of similar, in a similar vein, right, is that like as we, all of these models that we're seeing are getting quite close to this information boundary, right? And it seems like, the difference between, say, Llama 2, Llama 3 is eking a bit more out, right? How much more is there to eke out? And then I guess the follow-up to that is, what happens when you kind of just get so close that you get diminishing returns? Does this imply some limit to like what a model of a particular size can actually be capable of doing, right? Is that something like, what's your take on this, both of you?
Yeah, I mean, I think there's two answers to that. One is if we just assume the current training paradigm, right?
Yeah.
If we assume the current training paradigm, I think a takeaway from the paper is we're pretty much done, right? Is like pre-training is good, and models are along the bound.
We can go home.
For transformers.
The post-training picture is more complicated, where it's like getting this optimal compression of the pre-training data. Everyone's good at that. Getting this sort of more nuanced information about what makes for a good answer in a particular context, I think that has not saturated. And I think balancing those two, how you crowbar this sort of preference information in without ruining the kind of good compression that you got early in training, that is like really hard. But so that's sort of the first part, where if we assume the current training paradigm. The other part is saying like, look, we need the models to be smaller. From a compute perspective, the amount of compute it takes to do anything with these models is entirely prohibitive to actually training them, doing research on them, or using them on your phone in a meaningful way. The idea that when you want to ask like some idiotic question of ChatGPT about like, I don't know, like how to say something in Portuguese, that query spins up a bunch of like GPUs in Southern California in order to give me an answer that I should have been able to work out myself, right? And so if we could do that on a phone, that would be really nice. And what we can point to is we can point to like saying, hey, we think a huge part of the reason you can't do that is because at the parameter counts where that would be tractable, you really can't achieve the compression that it looks like you need. And so it's going, how do we shift that? And so I think in terms of the current training methodology, pre-training is saturated, post-training is interesting. In terms of downstream, what else we could do, if somebody can work out the model or the pre-training procedure that gets those 1B or like 100 million parameter models to the compression profile that we're seeing at like 70 billion parameters, that would be wild.
Absolutely.
I think this is where the real benefit of using using the information bottleneck framework and kind of putting in the effort to normalize things, like the power of the estimator to be able to compare across model sizes, across architecture. I mean, something we haven't talked about is like dense models versus mixture of experts. Things are changing in architecture terms. The estimator and the technique can be applied to these straight out the box. It's not. It's completely architecture agnostic. So it gives us a way of making these comparisons, which I think until now we've kind of has essentially been behavioral. And as Henry says, I'm very interested in this idea of efficiency and kind of, you know, it feels like it's fun to kind of push the boundary of what can we do with these models in terms of behavior and kind of power. But from a practical, I guess, kind of more long-term view, you know, we know these technologies are useful. Currently, they're pretty expensive to train, run, etc.
Yeah.
Can we achieve the same results with a much smaller footprint? And that, to me, that's where the really interesting stuff lies. How do we get there? No idea. But those are really interesting questions.
Yeah, absolutely. 100% agree. This is a really powerful tool to add to the toolbox of like ways of understanding what these models are capable of. So perhaps a good note to end on is, what are you currently working on? Are you extending on this line of research? Where can we find more about the work that you do?
Yeah, of course.
I mean, I guess I think the sort of natural roots are that we only looked at pre-training, or only pre-training data. There are some results about post-training in there, but the bulk of the analysis is what's going on in pre-training. And the other part is, broadly speaking, we use token diagram, trigram estimate. These are the kind of informations of interest. And in my head, this is kind of one corner in a 2x2 box. You know, you can extend in the sort of process direction and say, you know, we look at pre-training. What about post-training? SFT, RL, RLVR, off-pref, all of the kind of tools in the modern LLM toolbox, and more than I'm sure will come. What are they doing? How do they change the information structure in the model? What's going on? Maybe even why do they work? We have a bunch of discussions going on about. I think we know empirically what order to do all these steps in, but no one really has a good account of why we tend to do SFT and then RL and so on. And being able to frame this in terms of kind of change in information flow would be potentially really powerful. So I think that's one direction. And the other is in terms of what informations we're looking at. So we kind of touched on this with the language ID. But really you can kind of take this idea and run with it with any such label. And depending on your kind of quantity of interest or domain of interest. You know, in some cases, there are some very natural labels or distinctions, decision boundaries that it would be really interesting to look at and see how. I'm trying to think of a good. Well, Serafina, the last author on the paper works on safety. It would be very interesting to know, for example, you know, does the model learn the concept of harmfulness in pre-training? Does this evolve? Does it go up? Does it go down? You know, how do these types of information change throughout the whole training process?
Yeah, this is sort of like the current project is like project one of going, let's look at pre-training, let's look at the training distribution, and let's see what happens. And it's a nice place to start. And the original draft of this project also had a bunch of post-training analyses. It just turns out post-training is a mess. It turns out there's a bunch of different things that you do with different data distributions. It's poorly controlled. We don't know what different manufacturers are doing. And so it winds up being a more complex picture that we've increasingly put together. And so that's sort of the core next project. But yeah, I'm also working on some stuff that tries to understand learning more in the abstract, where we understand that there are cases where we get this sort of very nice compressive pattern, and there are cases where we don't. And there are a lot of decisions you make during training. Like, we forget in 2026 that like these models work because you're using a transformer with atom W that has a particular beta decay, and it has a weight decay, and you're doing all of these particular things. And it's essentially trying to understand how all of these contribute to learning as a whole. So that's part of it as well. There's also some more esoteric stuff. It's like the entropy estimator is quite fun. You can do it on quite a lot of different data. I'm currently working on some stuff with mouse embryonic data. It turns out that if you take gene expression space, an optimal compression of raw genes is cell type. And so it's trying to understand how you get higher order structures, and you get properties like the specialization of cells from like stem cells to tissues as this process of sort of like this gradual compression of the raw gene.
Wow. Fascinating. Fascinating. Thank you so much. Yeah. We'll make sure we link to